Morning, everybody. So thanks to those of you who are here. I have a slightly new setup, so it may take me a moment to get the table's slightly taller than the one I was using last week. But anyway, I'm a little unkempt. It's getting harder to get a haircut, probably, as you all know. Okay, so like I said last week, but if you weren't here, then you'll hear this for the first time. What I intend to do on the Tuesdays is usually talk about the homework problems, and the homeworks are always meant to be a setup for that week's labs. So this week in lab, we're introducing how to do the arithmetic operations on the ARM processor, and mostly we'll just be doing adds and subtracts. And then we'll put multiply and divide. Good morning, everybody. Oh, I gotta get used to good morning, looking at the camera when I say that. Thanks for being here. Okay, so we're gonna do add and subtract instructions on Thursday and also a little bit today. So my goal today is to sort of tell you, for the computer science perspective, why we trouble ourselves to learn these concepts at the processor level. I'm actually going to start with a C++ program to just make the point for you, and hopefully it cooperates with me. So there's a whole bunch of questions about flags, registers, and a carry, and negative, and overflow, and we'll get to all of those things. But the important underlying concept is to understand that when you're working with any data type, but for now let's just worry about integer data types. So we have unsigned integers, which can only be from 0 up to some maximum value, and we had a question on last week's homework. So for example, an unsigned 8-bit integer goes from 0 to 255, and that's all the more values it can store, because at that point you run out of bits to store any greater values. And if you need a value higher than 255, then you have to sort of graduate yourself up to at least a 16-bit integer, where you go now from 0 to 65,536, 535, and so on. And if that's not big enough, then 32-bit integer. So the real point of all this, to me anyway, is to get comfortable with the idea that data types have limits on computers. This matters when you're programming, of course. It also matters when you're selecting data types for your variables. What range of values might I need to represent, and what's an appropriate data type to select? So I'm going to start by writing a C++ program to demonstrate this. I'm going to switch this to, but I'm going to go ahead and let you watch me build it all the way from scratch, so that you know why all the parts are as they are. So this is a C++ program. So the first include is for C standard integer. This gives me a broader range of integer types that I can actually code with, including 8-bit integer types, and that's what I want to keep this example sort of manageable. So anyway, that library gives me definitions for a variety of additional specialized integer types of different sizes, signed and unsigned. Also, I have a string, so I can do some outputs, and then I'll just do this sort of global namespace directive. So this is not assembly code, obviously, it's just C++. But the point is, oh, you can't see that right now, can you? Let me let you see it. Oh, no, you can't see it. Okay, all's good. All's good. Although I want that to be somewhere else, so let me move it. And then I want my terminal to show. So you can see me working. Okay, that's better. Okay, so I'm going to write a C++ program just to show you how C++ handles the problem of what happens if you run out of space for the integers that you're storing. And we'll just start with a really simple one. So in the C standard integer library, there is a type called uint8t that is an unsigned 8-bit integer. So the C standard int include gives me this data type, which is an 8-bit unsigned integer, which means it can only store values from 0 to 255. I'll just call it num1. And I'll set it equal to 0 to start. And then I'm just going to write a loop. So I'm purposely writing a terrible program just so I can get it up and running faster. So this is an infinite loop. But what I'm going to do is print out the value and then increment it forever. I'm also, though, going to give myself an input. This is in part so that when you get home to trying this, you don't get garbage. Okay, so I'm just going to increment it and press enter and increment it and press enter. I'm going to start it at 0. This being an unsigned 8-bit integer, in theory it can only go up to 255. So let's see what happens, what C++ does with that. This will just be integers.cpp. As a sort of setup for why are we doing this in assembly. It's not printing it out. Hold on just a sec. It's printing nothing out, which is interesting. Let me, well, that's interesting. Let me cast it into a regular integer and see if that helps. Okay, so there's it at 0, 1. So I'm going to press this a whole bunch of times, and what we're really looking for is, as we approach 255, what happens. Okay, it wraps around. Now this is what C++ is supposed to do, but I want you to notice that, like, if you were doing a program and you had an 8-bit unsigned integer and you did math on that integer that took it beyond the boundaries of what it can represent, it's going to wrap around on you, and that's potentially a problem if you don't know to expect that. So that's a lot of why we actually do all of the stuff we're doing this week, is so that you appreciate better when you're working in high-level languages that in most languages integers have limits. So it wraps around, and it'll keep doing that, which is actually a defined behavior in C++, by the way. So in this language, it's supposed to wrap around like that. But it didn't become 256 because it can't be 256. So in C++, the way it handles that problem is it simply wraps around to the start of the range. I'm going to go the other direction real quick. So I'll start it at 255 and then I'll back it down one at a time. Just to see the behavior going in the other direction. All right, so there's the 254, so I'll just hold enter down until it wraps back around for me. Down, 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 it's gonna get to 0 and then wrap around because it can't go into negatives because it's an unsigned integer. All right, so hopefully that makes sense as a setup. I'm gonna change this real quick, so I'll leave that one there as a breadcrumb for later, but let's make a signed integer. So a signed 8-bit integer can go from negative 128 all the way up to 127. So let's see what happens if I make num1 a signed integer, start it at the bottom of its range, and then count up one at a time until we get to the top of its range. So let's see what happens there. So here it's going up through the negatives. It's going to cross 0 here in a bit. All right, there's 0, 1, and then I'll just hold enter down for a while until we get close to the top. All right, so here's that 127. That's as high as it can go as an 8-bit signed integer, and it wraps around. So it's the same behavior, just because now I've marked it as a signed integer. That special sign bit is also being interpreted by C++ to mean, oh, this is a negative number. And you'd probably, I'm Control-C, by the way, if you copy this code, it's purposely infinite, so you have to hit Control-C to kill it. Okay, so that's kind of, pardon me, that's why we do these exercises in the architecture class, is so that when you're working at a higher level language, you have a sense of what the limitations are to your data types, in this case integers specifically. I'm still on coffee hour, by the way. By 11 I'll be tea and honey, probably. Okay, so that whole setup is so that you sort of understand why we do this in this class, is so that when you're operating at a higher level, you have a better sense of in this case, how integers work and what their limitations are. Okay, so that's step 1. Step 2 is we'll look at how do you actually do binary arithmetic. And the reason to do this is so that you can kind of see how the processor is actually calculating these things and why the numbers would wrap around like that. So here's the basic binary integer math rules. I put the 0b there just to remind you that this is a binary number. So let's just go single bits at a time, because you can get the rules of the math with that. Okay, so if you add a 0 and a 0 in binary, you get a 0 out. That makes sense. The math rules don't change, by the way. 1 plus 1 is 2. 2 plus 2 is 4. Just when you see the numbers in binary, they look a little bit funny. So now let's add a 0 and a 1. So again, the numbers are in binary, but that doesn't change how math works in the universe. So, oops. So the result here is a 0 and a 1, which is still 1, because the universe is still intact. So now a 1 and a 0. Which is just 1. Now we get to the weird one. Now you're used to doing this in base 10 in decimal arithmetic. It doesn't really change because we're in binary. That's supposed to be a 1. If you add 1 and 1, you still get 2, but the problem in binary is that you can't fit 2 Let me push those out a little bit. The value 2, so 1 and 1 is 2, but in binary, 2 is represented as 1, 0. So the thing to recognize here is I'm now requiring more bits to store the result than I was with the amount of bits I was requiring to have the inputs to the problem. So these are all 1-bit math problems. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1. But in binary, 1 plus 1 no longer fits in 1 bit. It now requires 2 bits to do that. So hopefully that makes sense. You're used to doing these carries like this, but we do call that a carry. So the output of that little piece of math right there is 0 carry a 1. Hopefully that makes some sense. But the result is 1, 0. That's 2 in binary because 1 plus 1 is 2. But the thing to note is that you now require more bits than you did before. So the C++ program I was just showing you shows you what C++ does when it requires more bits to store a value than it has available, is it simply wraps itself back around. So in C++, you'd end up with 0 again, because it would have to wrap itself back around to the beginning of the range, which for 1 bit is 0 and 1. So that's a carry. I'm going to do an 8-bit one that has a carry just to show you. So if I have 1, 2, 3, 4, I'll split the nibbles. 4. Okay, that's okay. So if I were to add that value to 1, hopefully you recognize that that ain't going to fit. There's nowhere that 1's going to be. So I'm going to sort of just talk the math and not write the math, and hopefully you can follow. So if I add this first column, the 1 and the 1, I'm going to get a 0. And I'm going to have to carry a 1 into the next column. So there's the 0, carry a 1. So now for the second column, I'm going to do a 1 plus 1 plus 0, which is basically 1 plus 1 is 2 plus 0 is 2. So again, I get a 0, and then I have to carry that 1 into the next column. And then 1 plus 1 plus 0 is 2, so I get, again, a 0, carry the 1, and hopefully you can see where this is going. So 1 plus 1 plus 0 is 2, that's a 0, and I have to carry the 1 again. Now I'm at the break in the nibble. 1 plus 1 is 0, so I get 1, 0, which is 2, so I get a 0 in the output, and I carry the 1. 1 plus 1 plus 0 is 2. That's 1, 0 in binary, so I get a 0, and I have to carry the 1. 1 plus 1 plus 0, again, is 2. So I get a 0 as an output, and I have to carry the 1. And now I'm in the last column, and I get 1 plus 1 plus 0. So I get a 0 in my 8 bits of output, and then I have a carry bit because it didn't fit. Now if you do the binary math on this, by the way, if this were unsigned integers, this would be 255 plus 1 is 256, and if I were to put this bit right here in binary, that would be 256. So the data is actually still there. Anyway, the point to note here is that if this were 8-bit arithmetic, if I take the full-on 255 and add 1 to it, that no longer fits. I end up having an extra bit carried out that the result doesn't show. So in C++, you get this 0 back. And C++ more or less just throws away the carry, and it starts back where it left off, cycling around the range. Right, hopefully that makes sense. I'm not going to go to 16 and 32 bits because that just makes this, it's the same thing. Just takes a little bit longer. All right, so make sure if you do have questions that you ask them in chat. Otherwise, I'll just keep going. This isn't really a class where you have to memorize binary math. It's just useful to understand why do binary numbers do that. Why is my C++ value going from 255 to 0? It's because of the way binary arithmetic works, which is what the processor does. Okay, and this causes a carry. Overflow is, I'm going to sort of be a little bit gross about overflow when I talk about it, but carry is the way we describe the situation when we assume that our values are unsigned. But So let's actually, now I want to do it this way so you can see it. So here's my unsigned problem. So if this is unsigned, that value is 255, and this value is 1. Now if I take the same values, and I say instead, now let's call it signed. I don't know why I didn't put the 0b on there. Sorry about that. All right, so now let's do the same problem, but let's call it signed this time. In signed arithmetic, that's signed 255, or unsigned 255. This is unsigned 1. In signed arithmetic, this is signed -1. The way I knew that, by the way, is because if I invert all the bits, I get 0, and if I add 1, I get 1. So I know that this is the negative version of 1. That's how I did that in my head real quick. This is still signed 1. That's okay. Which in this case, by the way, do you notice how magically the math kind of just works itself out? But what I'm going to do, let's see if I can do this the way that I want to do it. Well, let's try it with 255. Do I want to do 255? Well, let's do 128 and 1. So I need to back this off. Actually, just do this. That's 128. So if these are signed numbers, remember this first bit means positive or negative. 0 means positive. So they're signed 127 and then signed 1. So I'm going to do the math on this and see what I get. So 1 plus 1 is 2, which is 0. Carry a 1. Same thing that we had before. So that's 2. Carry a 1. That's 2. Carry a 1. That's 2. Carry a 1. You know where this is going. I think probably. Most of this part's just a terminology thing. All right, I'm going to stop doing that part and hopefully you can just follow me. So that was 2 carry 1. This will be 2 carry 1. This will be 2 carry 1. This will be 2 carry 1. And then this one's going to be carried a 1 all the way down here. So that's actually going to be 1. So the trick here is that these are positive numbers. 127 and 1 are positive numbers. And yet when I do the math on them, I get a negative sign bit. Actually, in this case, yeah, that's a problem, is it? Because I can't represent negative 128. So anyway, the processor will recognize that I started with 2 zeros and ended up with a 1. Anyway, we call this situation overflow. Because I started with positive numbers and I added them together and I ended up with something that looks like a negative number, which in theory can't exist, can't be. Now if we were to render this, well, I'm not going to worry about that. But anyway, hopefully sort of everyone gets the point here. When you're, if you assume that you were starting with signed values and you take 2 signed values and add them together and you end up 2 positive sign values and add them together, and you end up with a negative number, that's something's not right. So we call that overflow. So when we're doing unsigned math, where the programmer knows that these are intended to be unsigned values, when we get a doesn't fit situation, we call that a carry. When we're doing signed arithmetic, when we get two positives make a negative, or two negatives make a positive, something that can't be. We call that overflow. Now, I'm simplifying a little bit. And again, this isn't something we have to dwell on just a whole lot. I just wanted you to have some sense of what carry and overflow mean. So carry for unsigned values means they don't fit. And overflow for signed values mean for some reason two positives made a negative, or for some reason two negatives made a positive. This does not matter when you're programming in C++, because C++ has already defined what it's going to do in these situations, as I showed you. But when you're at the processor level, just kind of understanding how the processor actually does the math is a little bit of insight. Okay, so anyway, that's the words we use to describe those situations. I will say, by the way, the processor, on the ARM processor, everything is assumed to be in Tues complement. But at the end of the day, the processor doesn't actually know if you intend for things to be signed or unsigned. It's just taking bits and it's adding them together and getting results. That's all the processor actually knows at the end of the day. You, the programmer, have to know what your data means and what could happen when you do math on it, if that makes sense. If it doesn't, we won't kill ourselves about it. Okay. Anyway, so binary math, unsigned math that doesn't fit, the result can't fit where it's supposed to go, that we call that a carry situation. And signed math, where the result kind of doesn't make sense, like two signed values make two positives make a negative, or two negatives make a positive, we call that overflow. That's just things to know. At the C++ level, the thing to know is if I keep adding 1 to an int 8, once I reach 127, I'm beyond the bounds, and in C++ it's going to wrap back around to the start of the range, which is negative 127. I'm not going to do it here, by the way, but one experiment you might do is, instead of adding just 1 at a time, add 2 at a time or 3 at a time and see what happens in terms of the expected behavior. Okay, so that's a little bit of setup before I go look at the homework problems specifically. All right, there's a few of you here. Thank you for all the good mornings again. If you got here since I said good morning to everybody. It's my intention, by the way, to not go past 45 minutes or 50 minutes. So I'm going to do my best to do that. Okay, homework questions. We are on homework 8. I'll give you the fancy words for the carry flag. In fact, I'll just go get them while you're watching. Wait, can you see this anymore? You probably can't, can you? Okay, let me get the browser back where you can see it. Okay, so I'm going to do these homework problems. Part of my meta here, by the way, is to help you sort of find sophisticated answers for yourself to brand new things that you've never seen before. So in the future, it would be nice if you were capable, like you got to the point where you were comfortable in hunting down a sophisticated answer for this question. So what is the carry flag and how is it used on the CPU? So I just kind of showed you that the carry flag is a way that the processor signals that the result of an addition doesn't fit. Is kind of the unsophisticated way to say it. The sophisticated way to say it, I'll just go here. The sophisticated way to say it is with these words. So in computer processors, the carry flag, or the C flag, is a single bit in a system status register used to indicate when an arithmetic carry or borrow has been generated out of the most significant ALU bit position. Now that's a lot fancier way of saying I added two numbers together and they didn't fit where they were supposed to. In other words, I added two 8-bit numbers together, but the result doesn't fit in 8 bits. We saw that because there was an extra bit sort of carried over that we had nowhere to place it anymore. So that's a good answer right there. A good sort of college-y answer for this problem is those words from Wikipedia. Now we're coming up to the flags here in a second. So what we haven't talked about yet is the fact that the processor actually has a register where it flags this information as it's doing math. So whenever you do an add instruction, which we'll look at here in a moment, the processor actually will tick off these flags indicating what just happened as a result of doing the add. So if I were to do the addition problem on the ARM processor I did earlier and the processor realized, oh, there's an extra bit that didn't fit, it actually will tick on the carry flag saying I had an extra bit that didn't fit. Okay, the second question. All right, so thoroughly explained from the reading the example of adding 255 to 255. The main thing for you to sort of take away from this is that you ought to know that ain't going to work. Adding 255 to 255 can't fit. And because that's so, it's going to generate a carry. The processor is going to recognize, oh, that's too much data for the space provided. Let's see if that's actually in this same place. Yeah, so in the uses section on the Wikipedia page, there's actually an example. You might be noticing, by the way, this is how I write my questions. I sort of do the reading myself, and then I find what I think are kind of interesting things to know about the situation. Pardon me. And ask you a question about it. So here's the answer to that second question. Here's what happens when you add 255 and 255 together. The result is 510, which is more than fits in 8 bits. If you were to do the math, then you'd end up with this pattern, but there'd be an extra carry bit. So what it's telling you is that the result you would see is 254, but the processor would also tick on the carry flag saying, hey, there was an extra bit here that didn't fit. So that's the answer to the second question, is that paragraph right there. You could pretty this doesn't read real pretty right now, but hopefully you get the idea. Okay, so that's hopefully everyone sort of gets the basics that when you're doing integer arithmetic, sometimes the results either don't fit or they don't make sense. And the processor can recognize that. So the processor will recognize, oh, I have this extra bit that doesn't fit. So I will tick on a special flag so that the programmer can come back and discover, oh, the result didn't fit. The processor also can recognize when the result doesn't make sense. Adding two positive numbers should not make a negative number, and the processor will recognize that and tick on a special flag so that the programmer can go discover it. One thing to note before we start talking about these flags is that the programmer has to go check. So when you do math, you have to go check if it is a concern of yours as a programmer, like it could be that was the result won't fit. You have to go check these flags in code, and we're going to spend a lot of the rest of the semester doing that. But these flags on the processor are how the programmer can go back immediately after doing math to check to see if there was a problem. Like, oh, the result didn't make sense, or the result didn't fit. That kind of stuff. I'm going to go check for questions. Hopefully we're still doing okay, everybody. Okay, so now we're going to add in, how does this work on the processor? Like, where do you look on the processor to discover this information about whether or not an instruction, an arithmetic instruction caused carry or overflow? And where the processor does that is in the program status register, which I asked you about earlier in the semester, and then you probably long since have forgotten, but I said at some point we'll come back and revisit the program status register and talk about what it's for and how you use it. So this is a register that's on the processor, and it's organized different than all the other registers. So for example, R0 is just 32 bits for you to use however you want. The program status register is special, and I'm going to click this status register link. Let me go back. I'm clicking this second link. This register on the ARM processor is special because it's not just 32 bits of whatever you want to do with it. It's 32 bits of predefined meaning. And I'm in the, I'm on this Hey Rick site has got some good basic ARM. But if you scroll down the status register page, you'll come to this bit allocation section. And this tells you how the individual bits are used by the processor. So it's a 32-bit register, like all registers on our ARM processor are, but they're not just anything. So for example, this 2 to the 31st bit right here, that is the negative flag. So when you do math, and we're going to do it in Lab 8, when you do math on the processor, let's say like you subtract 1 from a number, if the result is negative, the processor will actually recognize that and turn on this 1 bit in the program status register. And what that allows you to do as the programmer then is to immediately turn around and check to see if negative is set, and then you can respond to that if that's important to you in your code. Bit 30 is the 0 bit. So that's used for some comparisons and things, but you can also sort of, if I subtract 1, if I do a subtraction instruction and the result is 0, then this bit's going to be turned on by the processor saying, hey, the result that you just got was 0. The 0 bit is also used in comparisons, by the way, so the way the processor knows if two values are equal basically is to subtract one from the other, and if the result of that is 0, that means they were the same value. But the way the processor actually notes that is by flicking on this 1 bit saying, hey, that was 0. Bit 29 is carry. So that's when you add 2 unsigned integer values together and the result doesn't fit. Then you get a carry situation. And then bit 28 is overflow. And that's the situation where you're working with signed integers and you add 2 positive signed integers and you get a negative, or you add 2 negative signed integers and you get a positive. The processor will recognize that can't be right, and it will flag that as an overflow. There are other bits that also have their meanings, but the only ones that matter to us are negative, 0, carry, and overflow. That's the only ones that matter to us. And those are enough to give you some experience with the program status register flags. Okay, so the question is, briefly describe negative, 0, carry, and overflow. I'm not going to do this. Well, I might. Anyway, the answer is right here. So on the status register page, under bit allocation, there are descriptions of those bits. Now, I just kind of described what they are, but here is text descriptions of them. So what I did is I brought these. I'll show you how I did it. Here's my answer as I sort of formatted it off that page. If I can stretch that out so you can see it. So that's how I did it. 1 negative. That's the same words, by the way, as on that status register page. 2, there's the 0 part. 3, which I broke down into sections A, B, and C, and D, actually. So there's 3A, that's the first bullet point, 3B, second bullet point, 3C, third bullet point, and so on. And then number 4 is overflow with all those words in it. We have not talked yet about how do you see this stuff, which hopefully we have a few minutes to start on this morning. How do you actually see these bits? Sip of coffee. This is getting tepid. I don't know what you guys do to get yourselves up and running in the morning, but I put myself just this side of shaking with caffeine to get going. Okay, so we've talked about sort of binary arithmetic and why is it that, like, how do those ranges of values work in binary, and what happens if you add 2 values together and the result is bigger than the space you have to fit it in. What happens if you add 2 positives and the result looks like a negative? That's sort of all work that the processor, when you're invoking instructions, will track for you and set flag or status register bits to signal to you, the programmer, that these things happen. Now we haven't looked at how do you actually check to see that signal happened, but we're going to do that here in a second. Okay, phase 2 is the basic instructions for doing math. So fortunately, I mean, it doesn't feel like this all the time, but fortunately, a lot of the arithmetic instructions are just what you'd think they are. So how do I say that R0 equals R1 plus R2? Well, that's the add instruction. The destination goes first. And then the 2 arguments. So that instruction that I just wrote means R0 equals R1 plus R2. That's it. All right, the instruction that translates the expression R0 equals R1 plus 1, so that's also just the add instruction. The destination is R0, and I'm going to add R1 and the immediate value 1. That's all that is. That's decimal 1, by the way. I could have written it as hex 1 or binary 1, because those are all the same thing, of course. Yes. So the first R is the destination. So if you look at the documentation, the way they'd write this is add. And this part means the destination register, and then it'll have like an R source register and an R source or immediate is how they might write it. So what this means is that's where the result goes. That's the destination or the output where the result is stored. And then you have source values, which is a register that contains source data and a register that contains source data or an immediate value. And what we call immediate values in assembly programming, we call constants or literals in high-level programming. Hopefully that answered that question. So those two, number 4 and number 5, are just there to sort of expose you to what the instructions are supposed to look like. Actually, let's go bring up this add link right here at the top of the page. I'm going to open that in a new tab. Okay, making sure that you're still seeing what I'm seeing. So here's how he writes it. So you have a destination and then 2 operators. And then he actually, I don't know if you're probably now noticing, if you hadn't already noticed, oh, I just wrote those same questions basically with a slight variant to them. So the first register is the destination where the result goes. Okay, that's 4 and 5. 6. Okay, so now 6 introduces, I'll come back to that in a second. So in ARM, if you do a regular add instruction, you're basically telling the processor, I don't care if there is a carry or an overflow. So the regular add instruction will not set the result, the flag, the status register bit or the flag bit to indicate an overflow or not. So this add instruction, if you use it this way, means that you will get no indication from the processor if there was any kind of a problem. So you might ask, well, why would I do that? Well, sometimes I'm positive I'm not going to have a problem. Like I have start with 0 and I'm adding 1. If I'm positive I'm not going to have a problem, then I may not care if the processor tracks whether or not there are issues. So the regular add instruction means the processor does not track carries and overflows. Now if I use add s, which is what number 6 is asking about, that means that I want the processor to track issues. Meaning if there is a carry or an overflow, the processor will set the appropriate flag in the status register. But you'll notice that the instruction setup is no different in any other way. So this is still, R0 gets the result of adding R1 with R2. The difference is by adding the S on the end of the instruction, now the processor will set the program status register based on the result. So if there is a carry or an overflow, then this instruction will allow me to detect it. If we go back to this add, this HeyRick page, notice that he sort of documents both instructions in one place. So, and he says here, if the S bit is set, if it's add S as opposed to just add, then the negative and 0 flags will be set, and the carry and overflow flags are set as needed. So if you take the S off, no flags are set. So you can't use any of those status bits as a programmer to check the result. If you put the S on it, then you can check the status bits to check the result. Okay, so the instruction that translates the expression R0 equals R1 minus R2, that's this link. But you can probably guess at this point because the setup is the same. So it's just sub. The destination or result goes in R0, and then of subtracting R1, of doing R1 minus R2. Number 8, also a sub. R0 equals the result of R1 minus the immediate value 1. Which again, I could do, I could write that as hex, or binary, or decimal in code, doesn't really matter. Like the add instruction, so for number 9, it's just saying, what if you're interested in checking those status bits? Then you have to tell the processor that you are interested. So if you put the S on the end, the processor will now tick off the appropriate flags based on the result of the operation. But otherwise, the arguments are no different. I don't know why I have number 10 there, but I'll go ahead and cover it. Anyway, if I go to this page, the sub instruction on this ARM wiki, so notice that it documents both in one place. So it's useful for basic subtraction. And then sub s, where's sub s? Oh, here it is. If the s bit is set, then the negative flag is set, the 0 flag is set, and the carry and overflow flags are set as appropriate. And again, for most of you, this is kind of a one-off experience, so I just want you to have some insight into what actually goes on under the hood when you're writing in a high-level language like C++. In C++, the defined behavior is to wrap values around on themselves, so you usually don't really have any concern about any of these kinds of things in a language like C++. So RSB, I think I just have it there because I find it to be I know why it's there, kind of, but it's just sort of a bizarre thing to me. So I didn't actually end up asking you about any of these others, but let's go look at RSB just for giggles. Notice, by the way, so this is another math instruction. It's reverse subtract. And if you use it with the S, then you get the flags telling you if you had a negative result, if you had a 0 result, if you had a carry or an overflow as appropriate. The only difference is that it treats the operators backwards. We're not going to do this yet, but the reason why these exist is so that you can do things like this example, but let's not worry about that right now. All it really means for our purposes is that you have to understand that the operators are reversed. So, the way I would probably answer this is I would take that. So RSB you do reverse subtract. The destination is still, but now you reverse the arguments. I have a fancier answer that I'll show you, but that's all reverse subtract does. That's mostly just an exercise in going and reading some documentation. There are applications of it, but not in our class. One of these days I'll change that out for something that I like better. Anyway, there is a reverse subtract. It just seems really weird that it would exist, but it does exist. So you can imagine they probably wouldn't have created it unless there were applications for it. Anyway, the point is that the two operators, the two operands are reversed in their meaning. So to do R1 minus R2 with reverse subtract, you put the R1 second. My fancy answer to this looks like this. There's my fancy answer to that question. Still subtracts one value from another. The difference between it and the subtraction instructions is that the second operand is now the thing being subtracted from. That's it. Oh, okay, so good question. Do you have to put the pound sign on 5 and 8? With our assembler, that's optional. So if you like the way that looks with the pound symbol on it, that's fine. But with our assembler, our GNU assembler, it's happy if you leave off the pound sign. So you can do with the pound sign or without the pound sign. Those are both considered legal immediate values in our code. So you can do that for number 8 if you want, with or without it. Those are equivalent, and then the same for number 5. We're at 9:27. I wanted to do lab 8, but I think, yeah, we're gonna do some wiring. Let's have a quick peek. I'm gonna plan while you listen, because I thought I might finish that faster. Lab 9, which is what we want to work on Thursday. All right, so lab 9 uses the same circuit as lab 7. So hopefully you built this circuit and you didn't take it apart, because we're going to use the same circuit on Thursday, which means I'm not going to wire it. And that should mean that I can do both labs on Thursday, I hope. Because I don't want to make you sit here for huge amounts of time. So lab 8, if you want to have we're going to do lab 8 and lab 9 on Thursday. We'll start with lab 8, which does not require a circuit, it just requires the board. So we'll go through and we'll just sort of practice using the add and subtract instructions, and we'll look at the program status register and see what it does. And then lab 9 will be the longer one. So I hope I can do lab 8 in 15 or 20 minutes, and then lab 9, hopefully I can do that in 30 or 40 minutes. Usually I underestimate these things, but that's my plan, is to do that. But lab 8, all you do is connect the circuit board. So I'll show you real quick if you want to get a head start on us. Here's what lab 8 is going to look like in terms of the hardware. Bert Cam. So let's get it. Let's do it, man. Okay, so anyway, that's lab 8. That's it. There's no circuit attached. It's just going to be the board. We're just going to compile some code and run it on there, and then we're going to use the GDB program to inspect the registers and to inspect the status register, so we can get accustomed to how the processor is actually, what does the negative, what does the 0, what does the carry, what does the overflow bit, how do you see that? What does it look like on the processor? So lab 8 will only have the board, and then lab 9 is the same circuit. Look at my hands blue in there. Anyway, lab 9 is the same circuit. So lab 8, and then lab 9 will bring this back and we'll connect it back up, and we'll do something different with that same wiring setup. Okay, that's lab 9. Okay, so I'm at my Q&A part, so I'm going to stop talking content and I will field questions if you have them. So if you're about to log off, we're going to start with lab 8 on Thursday and then do lab 9 right after that. So if you can help it, please do not change that circuit from last week. We're going to use the same board. Yeah, so, all right, so checking for, yes, there are efficiencies. I mean, I don't think it's an efficiency worth having if the status flags mean something to you. So my rule of thumb when I'm working is if I know I'm never going to have overflow and I know I'm never going to test those flags, where I forgot where I was talking. Oh, if I know I'm never even going to check the flags anyway, then I just use the add and sub instructions as an example. If I know that I do need to check those flags, then I do use the add s and the sub s and so on, so that I can check them. Okay, so an example of Well, I'll show you the most basic way, which is what we're going to do next week. Okay, this part's gonna sort of look funky at first, but it's a really cool thing. Oh, you know what? We have it in code already. Let me show you an example in code and see if that helps at all. Not that one. Let me see. Let me look at a recent lab. Did lab 7 have I need to find a lab that had a loop in it. What about lab 6? Yeah, okay. So, I'm looking at lab 6 here, Vince. So you can see an example that we've actually been using the flags and what that looks like. So this is the lab 6 solution code, but I'm down at the delay loop at the very bottom here. And it is using the flags. Okay, so here's the delay loop, which is the same delay loop we use all the time. But notice I set up, this is a countdown value, so that's some large value in R4. And then I'm using the sub with S instruction. So I'm subtracting 1 from R4, but I'm also asking the processor to set the status flags for me. And the reason I'm doing that is because I want to know when that gets down to 0. Now this doesn't look like that's what I'm doing, but this branch instruction, oh, you can't. Oh, that's right. Sorry. Sorry about that. I'll go back and start over on that part. Okay, so now you should be able to see. So I'm looking at the lab 6 code here. Thanks for the heads up. I still had the browser showing. Yes, so the BNE is a way to check the 0 flag, basically. So what BNE, so that means branch not equal. But what that really means is the result of the prior instruction did not yield a 0. So what this branch not equal actually does is check the Z flag, which this is a funky thing about checking the flags, is that you almost never do anything that looks like you're checking the flag until you get used to it. So this branch not equal, following this sub S, it's checking the 0 flag. And if the 0 flag is not set, then I branch back and continue the loop and keep subtracting by 1. So that's how a lot of the flag checks are going to look. And we'll see other examples of it later in the semester, but a lot of them are going to look, they're going to be branching instructions based on some condition. And the condition determines which of the flags is being checked. So I don't know if that makes, hopefully that makes some kind of sense, but this is what the flags checks will often look like. Now I'm going to do one more example. Let me give you one more just real quick example. Another way that we often will set flags. What am I in? ARM, right? ARM. One last example. So sometimes we'll write a compare instruction. Let's just say we're going to compare R0 and R1. So compare is actually a sort of a fancy instruction that does some math under the hood. And then what we often will do is branch to some looping location. So what this means is, what actually happens in a compare is usually that one's subtracted from the other. So I'm checking one of the flags. And what I'm checking in this case is the 0 flag. And based on what the 0 flag has been set to, then I either do or don't branch or jump to some location. So hopefully that sort of helps. And thanks for pointing out I didn't have the screen showing. back that off. I'm sorry, I know this is kind of doesn't make for exciting broadcasting, but I'll just sort of occasionally prompt you with, I'll just sort of sit here quietly and answer questions as they come in and give it 5 or 10 minutes, and if I haven't gotten any, then I'll assume we're all okay, and I'll probably shut down the broadcast and post this video and rest my voice for the next meeting. I hope you guys are. Thank you. Yeah, you too. Hopefully I'll see you again on Thursday, or at least you'll have a chance to see the video. Hopefully all you guys are finding, I don't know if you're feeling all that cooped up in your houses, but if you are, hopefully you're doing something to manage that. Get outside. That kind of thing. I've just been walking around the neighborhood between these broadcasts to get out of the house a bit. Thanks. See ya. Hopefully I'll see you again on Thursday, or if not, then sooner than later. See you again. Okay, last call. Okay, I'm gonna shut down. You can email me with questions or ask me when I'm back on Thursday. I will be here on Wednesday morning, starting at 10 until there's basically I've given everyone a chance to ask and have their questions answered. So I'll be back here at 10 in the morning for just anybody can come in and ask me questions about any of my classes, and then your class again I'll see you at 8:30 on Thursday morning. So thanks for being up so early. I'm having to set my alarm too, but I don't have the commute anymore, so at least there's that. Okay, everybody be good and be well, and I will see you on Thursday or tomorrow if you come in for the Q&A.